Good morning. Good morning and welcome to another installment of Inorganic Ventures 2023 webinar series. My name is Michael Newman and I'm happy to welcome you and speak to you briefly about the webinar and our presenter today. I would like to state at the beginning that these webinars go hand in hand with our value proposition of being chemists working for chemists. In these days, when the availability of technical support and resources are becoming more and more scarce, Inorganic Ventures is proud to keep providing the analytical market with resources to increase knowledge and provide know-how on topics germane to the industry. We are really excited about today's topic and introducing our latest product line, Primary Certified Reference Materials. Our presenter is Brian Alexander, Chief Technical Officer of Inorganic Ventures. Dr. Brian Alexander is an earth scientist specializing in geochemistry. His research has focused on radiogenic isotope and rare earth element studies of natural waters and chemical sediments, as well as trace metal analysis using ICP techniques. A native of Southwest Virginia, Brian received his Bachelor of Science in Geology from Virginia Tech and his Master of Science and PhD in Geochemistry from Penn State and Jacobs University in Bremen, respectively. As a matter of housekeeping, questions can be made in the chat feature of Zoom, and we will address each of these at the end of the presentation. Now, with no further delay, Brian, we're eager to hear what you have for us.
Great. Thank you, Michael, for the nice introduction. And as Michael mentioned, what we want to do today is to provide a little bit of the technical background regarding our new product line of PCRMs. And as you can see from the title of the presentation, we will be focusing on three elements: osmium, iridium, and ruthenium. It's possible that many of you may not be familiar with these elements. They're a little bit rare, not only in abundance, but also in applications. But for those who are working in the pharmaceutical space, particularly those who are interested in following the USP 232 or the ICH Q3D specifications, these elements are increasingly being used in pharmaceutical applications as catalysts. So what we have seen over the past 10 years or so is an increased interest in people actually measuring for these elements in a wide variety of samples. So what is different about these elements? At this point in time, there are no National Metrology Institute products available that provide traceability to the SI for these three elements. And the SI is the System International, which essentially establishes the quantities and base units that allow people all over the world to conduct accurate measurements and have a reference for those measurements. And traceability to the SI is critical for Inorganic Ventures because we are a manufacturer of certified reference materials. And what you've probably noticed is that these products that we're talking about today are primary certified reference materials. So there is a different level of technical expertise that has gone into manufacturing them. And we want to explore that during this presentation and also share with you why we think it was important to embark upon this work. The real reason is that, as mentioned, there are no SI traceable products available in the market currently. And so our motivation primarily was to enhance our own product line of CRMs. We wanted to be able to establish traceability for these three elements to the SI. And so we felt that this was an important research project for us to embark upon. And so the ultimate goal is that we are going to be creating primary traceable solution standards for these three elements. And it's not only going to help the kind of broader analytical community, but it will help us increase the accuracy of our own products, the traditional CRM line that you are probably most familiar with. So these primary certified reference materials will be differentiated from our normal CRMs through a higher level of kind of technical background and how we are establishing this traceability to the SI. As such, they may not be applicable for everyday use. And for many users, the normal CRMs that are available in our product catalog will be perfectly fit for purpose. However, these are designed for users that need extreme levels of accuracy. I mean, what you'll see in the diagram is that we have a couple of pictures. These are two of the products that are currently available for sale. This is the osmium and the iridium standard. These are all provided in sealed glass ampules of 10 milliliters each. And if you were to decide that you needed that very high level of accuracy, when you purchase them, they come in a box of 5 ampules per order. So what is a primary solution standard? It's a measured value that is obtained by means of a primary reference measurement procedure. And for our purposes, of all the primary reference measurement procedures, we are focusing on gravimetry, or measurement by weight. So this is a primary SI traceable measurement procedure, and the references at the bottom of the slide are just for the vocabulary of international metrology, where these terms are explored in more detail, and they're there for your own reference. So if you're in analytical chemistry, you probably are doing a lot of things by volume dilutions or weight dilutions, but fundamentally at the end of the day, you are reporting the quantity of an element in a sample, and you're reporting it as the weight or mass of that element present. So we really feel that this gravimetric approach, or measurement by weight, was the best way for us to follow as we were developing these products. So now it's important to talk a little bit more about what is SI traceability. So SI is the System International, or the International System of Units, which was established quite some time ago in the 1960s. And this was a culmination of many decades of work. And really, the rationale was that we wanted to have a common reference or playing field for all the analytical measurements throughout the world, so that when we compare results, we're all on the same page. So there are 7 base units in the SI, and they're listed in the table, and they all refer to the base quantities such as electric current, the length, amount of substance, or the one that we're focused on for this presentation, which is mass, or the kilogram. So why does traceability matter? We've touched upon this briefly, but really it's to maintain clear communication about your results. When you have traceability to a base quantity or a base unit, then everybody really understands what you're referencing back your measurement results to. And this allows us to compare measurement results and have confidence that we're really talking about the same thing. And it's really about accuracy, accuracy, and accuracy. We all want to be able to communicate our results and our measurement results and understand what it is we're talking about, and that we have the greatest confidence that they are accurate. Now, the concept of chain of traceability, we're going to come back to this at the end of the presentation, but this is a key thing that we want to come back to and focus on. You always want to try to shorten your chain of traceability, because ultimately what that means is that you will be able to reduce the uncertainty in your measurement. It's one thing to be accurate, but it's also important to know just how precise your measurements are, and that uncertainty is key in that regard. So how do our new product line of PCRMs establish SI traceability? As mentioned, the measurement procedure that we focused on was gravimetric preparations, or measurement by weight. This makes perfect sense for the business that we're in. We know that the kilogram is one of the 7 base units, and thus we're going to obtain traceability to the SI through the kilogram. So throughout this presentation, everything that we're doing is based upon weighing a substance, knowing what you're weighing very, very accurately, and by that process, you can establish traceability to the SI. So if you actually want to have SI traceability, there are 2 basic requirements. We've discussed the primary measurement procedure, and we're going to go into more detail in the next couple of slides regarding exactly what that meant in our lab and how we were able to work through that. The second requirement is the purity analysis of what you're working with. You really need to understand very well how pure the substance is. And if it's not pure, you need to be able to characterize those impurities so that you can correct for those. So with these 2 basic considerations in mind, we're first going to focus on that primary measurement procedure. So these are the details of the experimental design. We could have just made this up and done what we thought was best, but we have really been benefited by a great relationship with NIST. And one of the reasons why we felt it was important to produce PCRMs for these 3 elements was that over our conversations with NIST over many years, they were very forthcoming in stating that they were not going to be preparing NIST SRMs for osmium, iridium, or ruthenium anytime in the near future. We love what NIST is able to provide for the analytical community. The resources, however, are limited. And once we learned that there was no pipeline for NIST providing these primary reference materials, we decided that we were going to step in and help not only our own products, but hopefully the broader analytical community. And rather than reinvent the wheel, we simply borrowed a page from the playbook of NIST. And this was published in 1993 when NIST released the rhodium SRM as part of their 3100 series of spectroscopic standards, which are primarily used for ICP and some other techniques. So we took the approach and the methodology that NIST followed, and that's what we used for the osmium, iridium, and the ruthenium elements. So basically, we needed to determine the mass fraction of the metals in the starting material that we chose to work with. And the process is that we take these starting materials and we reduce them gravimetrically to the metal. And then we weigh the metal. And at a very quick glance, that by itself can establish traceability to the starting material. So what are some of the details of that gravimetric reduction? So we take the starting material, the salt for osmium or iridium, and we reduce it under high temperature with hydrogen gas. And this is just a picture of the muffle furnace that we use for this approach. And then once we've reduced the metal, you say, okay, all I have left is pure osmium or iridium. That's the assumption. And when we weigh that out, we can use that traceability through the kilogram and establish the link back to the SI. Now, this determined the mass fraction of the metal in the salt. Now, this process was fairly labor intensive, and so we really needed to make sure that we eliminated any systematic errors. And so the major systematic errors in this reduction of the salt to the metal was exposure to air or moisture and any static that might be affecting your ability to weigh something accurately on a balance. And so we see in the diagram all of the lab kit that was necessary for us to achieve highly accurate weights. We had to work in an oxygen-free atmosphere. We had to monitor the amount of moisture in the air and account for all of those sources of possible systematic error. Now, that is in a snapshot, the measurement procedure for weighing out the metal. But the second part of the requirements for SI traceability are the purity analysis of the candidate starting materials. And so we want to look a little bit more closely in how we ascertain the purity and where the confidence that these are pure materials came from. So we, over many, many years, have become pretty good at measuring trace metallic impurities. And so we use both ICP-OES and ICP mass spec on the solutions for these materials. And then once we had reduced the salts to the metal, we used inert gas fusion because we needed to make sure that the reduced metal, which we were going to weigh very accurately, was characterized well for oxygen, nitrogen, and hydrogen. And based upon this information, we could come up with a final purity calculation. So we took the TMI analyses using ICP and the inert gas fusion on the reduced metal, and we could apply corrections to the mass fraction of iridium or osmium in the starting material. And that allows us to come up with a final purity calculation. So throughout this entire process, it's important that we check our work. We need to know that the gravimetric reduction and the purity calculations would produce an accurate, traceable primary solution standard. So what we did is we used the purity calculations and we made a standard solution, and then we went and outsourced a second source of the high purity metals, which were also characterized using inert gas fusion. And then what we did is we compared these two solutions to make sure that we didn't make any mistakes in the reduction or in our purity calculations. And so this really was one of the primary ways that we were able to check our work, and it followed the methodology that NIST used when they were producing the rhodium SRM back in the early 90s. So for those who are familiar with ICP-OES measurements, this will seem very familiar. We had to have accurate matrix matching, internal standardization of all the solutions that were being measured, careful monitoring of some of the results such as washout to make sure that there were no memory effects. And we even eliminated any errors associated or uncertainty associated with pumping by using natural aspiration throughout the nebulizer. And then we just measured a lot of different things. So we have a large statistical database, which gives us robust confidence in the results. So what we finally ended up with is we took the candidate solution standards, and what we found when we compared them to the high purity metals, that we were less than 0.1% relative from the values that we were expecting. And so this is a great check on the work because it lets us feel that, hey, we didn't make any mistakes anywhere, and that what we have been able to obtain is an SI traceable primary solution standard. So as part of providing any type of certified reference material, it is important for us to estimate the overall uncertainty associated with the products. And this is required as part of our ISO accreditations. So we have done this for many years for all of our products, really. And we use a combination of cause and effect diagrams where we map out all the different sources of error. This could include things such as the humidity or hygroscopic nature of the salt. Is it taking up water? What is the overall stability of the material that we're working with? How homogeneous is the material? These are all folded into kind of the ISO framework so that we can provide an accurate estimate of the true overall uncertainty associated with the certified value. And this is part of an error budget analysis that hopefully all analytical chemists are keeping in the back of their mind. You know, what is the final measurement that I'm going to be able to obtain, and what is the relative uncertainty associated with that measurement? So as we get toward the end of the presentation, we do want to circle back to this concept of your chain of traceability. If you have a very high need for accuracy, then what you might find that these products are perfectly suitable for your use. And you might also, for other elements, be going out to NIST or another National Metrology Institute and buying a reference material for them. If you're going to one of these NMIs, typically what you're going to find is a reference material that is going to have about a 0.2% relative uncertainty. We use these materials every day to create our own certified reference materials. And for many of our products, the uncertainty associated with them will be in the neighborhood of about 0.5%. You as the end user might be purchasing from us or another supplier of certified reference materials. And what you will be doing is then taking those CRMs and preparing your own standards. Well, the relative uncertainty associated with those solutions will be higher. And this is the key point about the chain of traceability. Every time you perform an additional measurement, you increase the overall uncertainty associated with the result. So the concept of shortening the chain of traceability is really critical if the uncertainty that you require needs to be very, very low. And so this is something that we felt was necessary because since there were no NMIs producing certified reference materials or standard reference materials for osmium, ruthenium, and iridium, we felt that we really wanted to shorten that chain of traceability for these three metals, and that's what we've been able to achieve. So in summary, what we have been able to accomplish is that we have primary SI traceable solution standards available for osmium and iridium. The key benefit is not only for the broader analytical community, but it helps make our own products that are CRMs or perhaps custom products that we may be manufacturing for you more accurate in the process as well for these three elements. This short chain of traceability really ensures not only highly accurate results, but the lowest overall uncertainty associated with the measurement. And the certified value and the uncertainty for these products are coming again from this concept of a gravimetric preparation and the purity analysis that we described previously in the presentation. So hopefully you have found this information useful. And as always, we look forward to any questions that you may have. Thank you.
So when I started the the webinar, I mentioned that the questions can be put in the chat feature. That was an error on my part. It's in the question and answer feature of Zoom. So if some of you are looking for that chat feature and can't find it, it's the question and answer. So far, we have no questions posted there, but we can hold on for a couple of seconds here and see if we do have anything posted.
Right. And while we're waiting, what I will mention is that this presentation will be made available to all attendees and also will be posted on our website. So feel free to come back to us at any time in the future if you have questions about the material we presented today.
Perfect. And it sounds like we've, with that clarification, we started to get some questions here. So an anonymous attendee is asking, what is the shelf life of the PCRM? Is it similar to your other single element standards, or is it different because of the low uncertainties?
No, it's going to be similar. And ideally, well, since it's in a sealed glass ampule, the shelf life from a technical perspective is essentially unlimited. However, we are assigning a 5-year shelf life to these because it's consistent with the other CRMs that we provide.
Thank you. Another question popping up here is, why would I need a PCRM rather than a regular CRM?
Fantastic question, and I'm really glad that this was asked. I would say that for the vast majority of analytical work, particularly for ICP techniques, you do not need a PCRM. And the question I would ask in response to this prompt is, do you buy NIST SRMs as part of your everyday work? And what most people in many analytical labs will answer with is, no, we don't. There's a couple of reasons for this. One, they are expensive. Two, they only come in a single concentration of about 10,000 ppm. And three, the availability can be limited. We love NIST and all the NMIs throughout the world, but they have a lot on their plate and they may not be able to provide the products that you need when you need them. So these PCRMs are really meant to kind of fill the gap for ruthenium, osmium, and iridium because there are no direct traceable materials available in the market. The simple answer is really that for most applications, a traditional certified reference material will be more than adequate for your application.
And we have two other questions that just popped up here that kind of are related and that you may have addressed right there. But are there other PCRMs that you are working on? And the similar question is, are there other elements that no SRM exists for?
So yes, we're working on ruthenium. The initial concept for developing these was really to focus on osmium, iridium, and ruthenium. Osmium proved to be the most difficult one, and we did that first, of course, which really kind of provided a lot of the technical foundation for ruthenium and iridium. Beyond those three metals, we currently have nothing really under consideration that we would explore. To the question of, are there other elements for which there are no SRMs? I think this gets a little into, do you care about elements such as the halogens? Do you care about elements such as hydrogen or helium? And I think that for most analytical applications, and at least the industries and markets that we serve, those elements aren't really under consideration. For what we provide and for the feedback that we receive from our customers, there really are no other elements that you cannot get SRMs for, with one exception, really two exceptions, and these will be thorium and uranium. I can't speak for other NMIs, but NIST is, for all intents and purposes, discontinued the thorium and uranium SRMs that they used to provide as part of the 3100 series. This has a lot to do with the safety and compliance issues associated with those elements. So I hope that helps answer the question, but really these three products, the osmium and iridium and ruthenium, from our perspective, really flesh out and complete all of the kind of SRM type reference materials that would be available in the periodic table.
Thank you very much. An application question has come in requesting, can we get a couple of examples of applications where these PCRMs may be used?
We really rely upon our customers and the feedback we receive from them to kind of inform the answer to that question. As these are new products, the only application that we can speak of directly is in a research labs, in an international research lab that reached out to us recently for the osmium. I would think that the more direct application would be if you are in a highly compliant industry such as pharmaceuticals. And as we mentioned in the presentation, if you are having to test for osmium, iridium, and ruthenium as part of the USP 232 or the ICH Q3D specifications, depending on your application, you may very well want to look into using these PCRMs. However, I would circle back to really the biggest benefit in many ways is it made our products better. Our CRM products are now traceable and they're much more robust with that traceability chain. And I think that for most applications, my first recommendation would be try a typical CRM first. And if it's not what you need, then come talk to us. And it might be that a PCRM is more suitable for what you are trying to achieve.
Perfect. Questions flowing in now. Has IB thought about conducting any round robins on these CRMs, on the CRM materials, sponge, alloy to broaden the instruments available? Example, GDMS, SparkMS, and XRF.
Yeah, we would be happy to entertain any of those ideas. As part of any type of round robin protocol, the end user, whatever it may be, the different lab sites, what are you comparing it to? So this would be the fundamental question, is that if you were to participate in a round robin, you would be taking these PCRMs and you're comparing it to something else. So that's really the question that we would have is, what else are you comparing it to? Because again, we scoured the world and we were not aware of any directly traceable to the SI materials for these three elements. So we would be happy to entertain that, but that would be the fundamental question that we would ask is, what are you comparing it to, and is it SI traceable with a very short chain of traceability?
I'm going to put two questions together because they may go hand in hand. One, how do you deal with the memory and volatility effects for osmium? And two, how do you handle the washout for osmium in ICP techniques?
Yeah, that is a great question. I am going to borrow a little bit of information that other people in our organization are much more knowledgeable about. What we found for these sticky elements is that you need to use either in combination or singularly compounds such as thiourea or hydroxylamine hydrochloride. And there should be either one or two presentations or videos on our website that speaks about this directly. I do know that we have had a number of presentations on washout and memory effects. The question is absolutely fantastic because osmium in particular can have some severe memory effects. And again, I'm going to say that either thiourea or hydroxylamine hydrochloride, and I think it's thiourea, is really, really effective at helping with that. If you'd be kind enough to submit your contact information or reach out to us separately, what we'll do is we'll provide you with some of those presentations and videos that will more directly address that question.
The next question is this a reason why osmium and iridium are not included in C of A's for pure acids?
Oh, I think that is a fantastic question. There are a number of elements that are not included in C of A's for pure acids. And, there are different reasons. For osmium and iridium, I'm assuming that they're not included simply because there is very little reasonable expectation that they would be a common contaminant. These are geologically rare elements. You do not find them as common contaminants in any real lab that kind of normal lab operations that I'm familiar with. So I suspect that the acid manufacturers are just saying, we're not going to test for it because it would really, you just do not expect them to find them in any type of purification process for a mineral acid. Perfect.
That was the last question on the list. And I want to thank Brian. I want to thank you for your time in the presentation. The attendees, I want to thank you for always taking your time to attend our webinars. We feel that they are packed with information and useful. Please reach out to us. Continue to reach out. Some of the questions that were asked, if you want further information, please reach out to us with your with the clarification that you may need and your contact data so that we can get you those. And we look forward to seeing you at the next webinar. And thank you so much for attending.